Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Lou Lee with us today. Hi, Lou.
Hi, Frank. Yeah.
How are you?
I'm fine. How are you?
Good. What's your, where are you located at? What's your geolocation?
Oh, I'm in Shanghai. I'm a PhD student in Shanghai Astronomical Observatory, Chinese Academy of Sciences. Yeah.
So yes.
Now in China, it's on holidays recently, so I'm in my home, not in my office. Yeah.
Out of what is the holiday that's being celebrated?
Oh, National Day.
National Day.
National Day is holiday. It's a whole week. Yeah.
Awesome. Whole week. Gotta love that. Wow. Fantastic. So yes, people, we are on opposite sides of the world here, and we're doing this. So if we happen to do a little glitch on the audio or video, it's all good. We're going to keep rolling. Lou, what do you like to do for research?
Oh, my research covers broad topics related to the open clusters, including the binary stars, mass function, dynamical evolution, and the data mining sky surveys, such as Gaia, to find new open clusters. At present, I'm trying to build a comprehensive statistical model for open cluster photometry to measure the binary properties, fitting the isochrone, etc. Yeah.
Mm-hmm. You mentioned you were a grad student. When do you anticipate being Dr. Lee? When do you graduate? When do you become Dr. Lee?
Next June, I think. Next summer.
Okay, so
I'm writing my thesis now. It's not a easy job, right?
That's great. That's very good. Is that an espresso machine over your shoulder there? Do you have an espresso machine where you're at?
Yeah, espresso machine. Yeah. Anyway,
I have.
I love coffee.
Right here. There we go.
Ah.
So let's go ahead and get into it with that intro. So this is a really lovely paper. I liked it a lot when I saw it. And this is modeling unresolved binaries of open clusters in the color magnitude diagram 1, method and application of NGC 3532. And Lou, take us away.
Okay. This paper is the first paper of a series. It focuses on the unresolved binaries in open clusters. We develop a comprehensive approach that model the cluster members in color magnitude diagram as a mixture of single stars and unresolved binaries. You can infer the binary fraction and mass ratio distribution with high precision. We apply this method to the open cluster NGC 3532. The results show some clear evidence for dynamical evolution in clusters.
Okay.
Some of them are reported for the first time. In the future, we will cover more open clusters and more cluster properties, including the distance, age, and metallicity.
Cool. Okay. Very good. Okay. So where did you do these observations, or were these observations already done?
The observation data came from Gaia data release 2.
Okay.
Yeah, we use the photometric data. Yeah.
Yep. Very good.
We go through the introduction.
Yes. So we got the intro.
Okay. The open clusters are excellent laboratories for the study of binaries. First, it's generally accepted that most stars are formed in open clusters. Through the stellar dynamics like segregation, evaporation, and tidal disruption, most of the stars disperse to the field, and only 5 to 10% of the total mass of Milky Way are kept in clusters. And the majority of the stars are thought to form in binary or multiple systems. So the initial binary properties of stars place important constraints on star formation theory. Second, the binary deeply involved in the dynamical evolution of stellar clusters. So the binary properties can trace the dynamical status of stellar clusters. Yes, we have the color-magnitude diagram of the open clusters. So the open clusters have better measurements to age, metallicity, especially the distance, than the few stars. This is the extra benefits for us to study the binary population in open clusters. Open clusters covering a wide range of structure parameters, but the homogeneous determination of binary fraction and mass ratio distribution for a large sample are still missing. So most of the binaries are unresolved binaries. Some of them can be resolved by spectrum or radio velocity, but they are expensive and biased to the luminous stars, and the sample is incomplete. However, the photometric data is cheaper. It is easier to obtain. But for photometric unresolved binaries, we face a lot of challenges. First is the poor membership determination. But thanks to the Gaia data release 2, more precise kinematic data brings more precise membership. Second, we like statistical rigorous methods. So some people just made some attempts on very limited sample. Shall we go to the figure 1?
Sure. That was our model.
Yeah.
Algorithm. You're using Conan Feigelstein there. Okay, figure 1. Color. Okay, fire away.
The binaries we talked here are the photometric unresolved binaries. They lie on the main sequence, and they are apparently single stars that are actually double. We all know that single stars, single stellar population lie on an isochron in color magnitude diagram. And the location of a star is only determined by its mass. And the unresolved binaries broaden the main sequence to the brighter and the radar direction. The black dashed line is the main sequence, and different colors shows the different binary sequences with different mass ratio. So the binaries locate in CMD, determined by their mass of 2 stars, or we can say primary mass and mass ratio. The equal mass systems will appear 0.75 magnitudes brighter than the single stars on the main sequence, while the unequal mass systems will distribute between the 2 sequences. A broadly used approach to calculate the binary fraction, especially in globular clusters, is define the empirical threshold in color magnitude diagram to separate single and binary stars, like they arbitrarily define an threshold like Q equal 0.6, and divide the CMD into 2 regions and count the star in both single star region or the binary star region. This kind of method is arbitrary. It is difficult to determine the main sequence precisely due to the observational error. Moreover, it's unable to measure the low mass ratio binaries, since it's hard to tell whether a star in the region that near the main sequence is a single star or a low mass ratio binaries due to the observational error. So in this work, instead of distinguish whether a star is a single star or a binary, we propose a mixture model to model them together. Okay. Then we go to the method part. And the mixture model method can combine multiple components into a single probability density distribution. The cluster members are assumed to have a mixture distribution in CMD, like in figure 2. Figure 2.
Okay, it's a little too big. There we go. Okay.
Yeah, we fixed.
Okay.
We fixed first we built the single stellar, the distribution of single stars. Okay, in panel A, we fixed the isochron and mass function to get a single stellar population, the distribution of the single stars. And we add the binary population in panel B, which characterized by binary fraction and the mass ratio distribution. We use a single power law to describe the mass ratio distribution.
Okay.
The location of single stars follows the isochron. Their distribution along the CMD, in CMD along the isochron direction is determined by mass function. And the binary properties determine the distribution in perpendicular direction. And at last, we use the binary fraction to combine them together as a mixture distribution. And we convolve the observational arrow to get the probability density distribution of mixture model along with the equation 8. And according to this, we can solve out the fraction of binaries and the distribution of mass ratio simultaneously.
Yes. Question.
And
let me ask a question here. Does one worry here about, I mean, you've probably assumed that all the stars have the same composition here?
The member stars are assumed to follow a mixture distribution of single stars and the binary stars.
Right, but they all have the same.
For one
composition. They all have solar metallicity, for example.
Yes, the solar metallicity. For one open clusters, they have the same metallicity, age and distance. Yeah.
Okay. Just
right.
Okay.
Simple stellar population.
Yes.
Yeah. In the following, we validate our method with mock samples in section 3, I think. Figure 3. Yeah, figure 3. Figure 3. Yeah. Figure 3 shows how we make a mock cluster. It also may help you understand how we make the model. First, we have a given isochron and mass function, and the number density along with isochron determine the mass function in color.
Yeah.
And then we add the binary stars when given a binary fraction and the mass ratio distribution. At last, in panel C, we add the observational arrow to each star. So the mock cluster CMD is very similar to the real observational ones. This procedure is basically how we build a model to compare to the observations. We apply our method to one single mock cluster and use MCMC to infer the parameters. The counters are shown in figure 4. And figure 4 shows the fitting result of one single mock cluster. The blue cross is the 2 values, and the counter shows the fitting result, and we will recover them. We also made, for figure 5, we also made a set of mock samples with different binary fraction and gamma Q. Each group have 100 mock open clusters. In figure 5, the 2 values are in cross of gray dots 9. Yeah, the 2 values are in gray cross of gray dots 9, and the infer value are black crosses. So we can say our method is accurate and precise through this mock test. Then we apply our method to real observational data, NGC 3532. And this open cluster is a relatively young open cluster. Its age, like in table 2, its age is about 400 million years. Table 2, the basic properties of NGC 3532. And it is solar metallicity and 405 parsec away. It it has very little extinction. It is very bright in the southern sky. So we use it as an example to demonstrate our method. This in figure 7. These 3 panels show the basic properties of NGC 3532. The members are determined by the Gaia's paper and other work. Panel A is the spatial distribution. Red circle is the half number radius. Panel B is the proper motion distribution, and panel C shows the parallax. The members are highly concentrated in a geometry space, so we are very confident about the membership.
Okay.
When we use our method to the real data, the first problem we made is the parsec isochron doesn't match the data precisely in figure 8, panel A. We use parsec, but maybe due to the stellar model or the color calibration of Gaia's problem, the parsec isochron disagrees with the actual location of the cluster members in some magnitude range, like in magnitude 10. If we use this unmatched isochron to construct the model, we will get the wrong determination of binary stars that are not really are.
Right.
We will wrongly assume the single stars as the binaries and overestimate the binary fraction. As the workaround, we can directly use the main sequence ridge line from the data itself. Conventionally, people usually draw the isochron, draw the ridge line by hand, like free whiskey, F19. Here, the green line. This is very time-consuming and arbitrary. Panel B shows the residual between the ridge line drawn by F19. He is drawn by hand, manually, and the observational in color versus the magnitude. The difference is quite large and may also affect the inferred binary properties. Here we made an automatic method in using Gaussian process based on iterative trimming, which is objectively and fast. The result is shown in panel C, which the residual is centered by 0, which means the ridge line we found is matched data very well. But more details of this algorithm, Gaussian process, will be given in another paper, how to use the Gaussian process to find the ridge line. Yeah. Another problem is the result of binary fraction is very sensitive to the scatter of the main sequence. There is a degeneracy here. We cannot tell whether a star close to ridge line is a single or a low mass ratio binaries due to considering of the observational error. As shown in panel C, error is much smaller. Observational error given by Gaia is the blue shaded region, and the orange dash line is the real scatter we detect. Yes, the underestimation of scatter will lead to the overestimation of the binary fraction and underestimate the power index of the mass ratio, which means if we use underestimate scatter of the main sequence, we'll tend to have more low mass ratio binaries.
Yes.
Right.
I'm with you.
We fit the scatter of the main sequence in each magnitude beams in using the stars that bluer than the ridge line, which represent the single star sample. Yeah, we use a single star sample to fit the scatter of the main sequence. The scatter we get is the orange dash line. The large difference between the real scatter and the observational error can come from the non-negligible intrinsic scattering main sequence or underestimation of the observational error from Gaia. We don't know which we don't know the reason, but yeah, the observational error is underestimated. We put this actual scatter to build our model, and in order to get a more robust result, we take a measurement with the binaries of mass ratio larger than 0.2. Is the red line.
Okay.
That means the binaries with mass ratio lower than 0.2 are considered as single stars here.
Yeah. Okay.
We go to the result. We go to the fitting result of the NGC 3532. We use maybe figure table 3, I think.
Table 3, yep, figure, right, yes.
Yeah, we use table 3 is the empirical ridgeline and the scatter we found. We listed here. In table 4, maybe the result.
Okay. Slide to table 4 and figure 10. Here we go.
Table 4. Yeah.
Okay.
We use the sample. We use the sample of. We use the sample with the major mass between 0.5 to 1.5 solar mass. The bright end of the sample shouldn't be too close to the turnoff because the broadening effect near the turnoff is complicated by the stellar rotation. Our result shows the main sample there are about 27% binaries with mass ratio larger than 0.2. And the gamma is minus 0.1. This value is near 0, which means the mass ratio distribution is flattened. Yeah, it's a uniform distribution. This distribution is significantly flattened than the random pairing binaries. The random pairing binaries Q distribution is more likely have a gamma similar to its index of mass function, which is minus 2.35. This flattening effect might be a hint of dynamical evolution. We further divide the main sample to 2 bins with equal number according to their luminosity, G less than 50.0 magnitude. Yeah, the bright sample represents they have more high mass binaries. The fainter sample are the low mass binaries respectively. The orange counters in figure 10, panel A, shows the different result, fitting result of different subsamples divided by the luminosity. The orange counters shows the result of high mass bins. We see here the different result of different mass bins. The high mass end have higher binary fraction and a lower gamma Q, which means it has more low mass ratio binaries there. This result consists of what we know before because the binding energy of binary system is proportional to its major mass and mass ratio. So larger primary mass binaries were less affected by dynamical processing. Therefore, the larger mass end will have more low mass ratio binaries. So the binary fraction is higher and the gamma Q is lower. And we also divide the stars into 2 bins with equal number by the distance to the cluster center, which is the radius. We see here the result has a clear difference between 2 bins, a panel B in figure 10. In the inner region of the cluster the inner region is the blue counter, show a lower binary fraction and the less low mass ratio binaries. This is due to the more fierce dynamical encounters in the inner region. And maybe occur another effect that is the dynamical interaction. The number density is higher in the inner region, and we believe the 3-body interaction is more frequently happens. It will replace the light star in binaries by more massive stars. The star in outer region behave more similar to the field stars. So it is the first time in observation we found a mass and radial dependence with the binary properties. When we obtain the mass ratio distribution and the binary fraction with mass ratio over than 0.2, we can infer the fraction of high mass ratio binaries like a binary fraction with mass ratio over than 0.5 or 0.7. The table 4, the last 2 columns, we can clearly see the binary fraction with mass ratio over than 0.7 is almost the same in each subsamples. So this dependence comes from low mass ratio binaries. Therefore, this is an evidence for dynamical processing cluster, smaller binding energy for smaller primary mass stars or low mass ratio binaries, and more dynamical encounters in the inner cluster. I finished the result. I directly came to the conclusion.
Sure.
We established a comprehensive framework for open cluster in CMD, and this mixture model method is strict and accurate, can contain multiple components together. In the future, we plan to apply this method in a larger sample of open clusters to measure the binary properties, to fit in the isochron, even to measure the mass function. That's all. This is our work in this paper.
Cool. Cool. Thank you. So what do you think might be your next target cluster that you'll go after? So there will be a paper 2 in this series and a paper 3. So what are some of your other cluster targets?
We plan to use this method to a larger open cluster sample, like we plan in 100 open cluster maybe. To there has this open cluster must have very little extinction, the internal extinction, and the main sequence must have clearly seen in the CMD. If the internal extinction is very high, the main sequence will be very broadened by the extinction, internal extinction.
So you're going to be looking for
we plan
targets.
Yeah, I'm looking for the target. Yeah, the sample.
Very good, awesome.
And we plan to use this 100. Another project is we plan to use the open cluster to define to find the ridge line for each open cluster and to detect whether the discrepancy between the observations ridge line to the isochron, to the parsec isochron, is the real.
Okay, that'll be interesting. Might be interesting to try other isochron packages as well and see what that might do.
Yes, I tried the MIST, but the MIST the discrepancy is larger than the parsec. I don't know why.
I don't know why either. I'm just suggesting. There are. But okay. So
the discrepancy is large in the small mass end.
Okay. So in some sense, you chose which set of isochrons gave you the best result.
Yeah, I have to. I think parsec is the best isochron right now for me. Yeah.
Correct. Yes. I got it. Yes. Okay. Cool.
Can I use one more second to introduce a poster that I made recently? I sent you the poster I made for the AAS poster exhibition.
You certainly may. Give me 1 second to let you share the screen. And you may share your screen.
Okay.
Have to check on this.
Can you see my screen?
I certainly can.
Yeah, I'd love to do some outreach to use the plain words to explain what I did for the public. And I made this poster for the AAS poster exhibition. And at the last slide, I would like to introduce the sociology in the City of Stars. The City of Stars is the open clusters. The binaries is the couples. So in the City of Stars, many stars, like 30% of the stars are in marriage, they're binary systems. And we found that the most stable style of the marriage is the two-body systems. The open relations, the higher order systems will be destroyed by dynamics efficiently in the early stage of the open clusters. The marriage is fragile when you compare the standard mass to its wells of a star, that the marriage is fragile when you are both poor. That means you are both very massive, less massive, and you are much poorer than your partner. That means the binary have very low mass ratio. And if you live in the downtown, the inner region, well, there are too many temptations. So your marriage will be very fragile. But however, there is an exception. According to the Hedge-Hill law, the very loved ones, that means the hard binaries tend to harden. So if you are hard enough, so don't worry about this. Yeah, this is the interesting conversion of what we've done for binaries. Okay, thank you.
That is an awesome interpretation. That's great. Very good.
Thank you.
Thank you. So if you want to stop your screen share, we'll do a proper goodbye.
I stop my screen share.
All righty. Lou,
Okay.
I want to thank you so much for spending some time today talking about your lovely paper.
Thank you too.
Lovely interpretation, and I hope you enjoy the rest of your holiday there in China.
Thank you, Frank.
All righty. Goodbye, everyone. We'll see you on the next one.
Bye.
Bye-bye.